Welcome to our session. In this session, we'll talk about our work to build a scalable and distributed AutoML framework using array, and especially how we apply it to a lot of real-world time series forecasting use cases. First, this is the agenda for today's talk. We'll first share some backgrounds around array, AutoML, time series analysis, as well as analytics Zoom, the platform we have built our AutoML support on top of. Then we will share how we apply the scalable AutoML for time series analysis on top of array, especially a lot of real-world use cases. So first, the background. Analytics Zoom is an open source data analytics and AI platform. At Intel, we have been working for a very long time to bring AI to distributed big data. So previously, we have built an open source BigDL, which is a distributed deep learning framework for Apache Spark. The users can write their new big data and the deep learning applications using BigDL, just like any standard Spark application. On top of those deep learning frameworks like TensorFlow, PyTorch, BigDL, as well as big data frameworks like Spark, Flink, we have also built Analytics Zoom, which is a high-level analytics and AI platform. The goal is really to help the user seamlessly scale their AI applications from laptop to large-scale distributed big data environment. So this slide shows the stack, the technology stack for Analytics Zoom. As mentioned before, it is built on top of those deep learning frameworks, distributed data analytics frameworks, and it can run on a laptop, and without any code change, you can seamlessly scale to large clusters, whether it's a Hadoop cluster or a Kubernetes cluster. Inside Analytics Zoom, there are 3 layers. At the bottom layer, it is the so-called end-to-end pipeline layer, which is a horizontal layer that allows users to seamlessly scale their AI algorithms, AI models to large-scale big data environment. For instance, a lot of our users are running distributed TensorFlow directly in Spark to process very large data set. And then we also add array support in that layer too. On top of the pipeline layer, there is a so-called machine learning workflow layer, which try to automate a lot of the tasks to build the end-to-end pipelines. The AutoML support is one of the key features in the ML workflow layer. And at the top layer, we also provide a set of built-in models for, say, recommendation, time series analysis, computer vision, NLP, and so on. The user can use those built-in models in the underlying workflow or pipeline layers. They can also use any standard, say, TensorFlow, PyTorch, or Caffe models in Analytics Zoom. Next, my colleague Shengsheng will share more details on the time series, AutoML, and especially the AutoML support we have built in Analytics Zoom that have been used for a lot of real-world time series applications.
Okay, thanks, Jason. Now let's come to time series. So first of all, what is time series? In short, it is a series of data that is observed sequentially in time. Examples of time series include stock prices, sales volume, and several monitoring metrics. Time series forecasting is one type of time series analysis that uses the history to predict the future. Besides pure forecasting purposes, it is also very common to use forecasting as a pre-step for online anomaly detection. In that case, we first forecast the future value, and if the new value diverges too much from the forecasted value, it would be considered anomaly. There are many applications of time series forecasting. For example, demand forecasting can be used for inventory management and resource scheduling. Anomaly detection of sensor readings can be used for predictive maintenance of high-value equipment. And you will see more applications in the following sections. There are actually various approaches to solve this forecasting problem. Traditional methods such as autoregression, exponential smoothing, and ARIMA are widely used in the real-world applications. They are relatively simple, but are not very good at capturing complex temporal dynamics and relationships across time series. Recently, machine learning and deep learning methods are becoming popular. Some deep learning methods for sequence modeling have been applied to time series, such as LSTM, GRU, temporal convolutions, and attention. Compared to traditional methods, these new methods are often more data-driven, and there's evidence that they can outperform traditional methods in several well-known competitions and real-world applications. Although machine learning can work well in forecasting, training a model is not an easy job, especially for those who are not so experienced in this field. And that's why we want to utilize AutoML to make it easier and more efficient for our users to build their time series forecasting applications. AutoML technologies can be used to automate various stages of the machine learning pipelines. As shown in the figure, stages such as feature engineering, model selection, optimization, and evaluation can all be automated by AutoML. Essentially, the task of AutoML can be perceived as to optimize a target metric within a given budget. Modern approaches consider this as another optimization problem and uses far more complex methods to solve it than simple grid and random search. AutoML can be used to search for hyperparameters as well as model structures in deep learning. When we're building AutoML support in Analytics Zoo, we finally choose RayTune to be the backend of our hyperparameter tuning module. Ray is an open source distributed framework for emergent AI applications, open source by RISELab. And RayTune is one of the libraries on Ray for scalable experiment execution and hyperparameter tuning. Besides RayTune, there are also libraries on Ray, such as RLlib for reinforcement learning and RaySGT for distributed training. For better integration of RayTune and other emerging Ray libraries and applications, we developed a feature in Analytics Zoo called Rayon Spark. Rayon Spark allows users to directly run Ray programs on existing big data clusters, such as Yarn or Kubernetes, without the need to install dependency libraries or manage a separate Ray cluster. And users can easily integrate Ray programs into an entire big data pipeline. For example, you can first use Spark to do some pre-processing on the distributed data, and then use Ray program to continue distributed training on the output of Spark. There is little data transfer or format conversion required during the process. Okay, now let's dive in a little bit into the Rayon Spark internals and see how Rayon Spark does what we just mentioned. We know that to run a Spark program on a Yarn or Kubernetes cluster, we need to first create a Spark context object on the driver node. And then Spark context is used to launch multiple Spark executors to run Spark tasks. Similarly, Rayon Spark also creates a context object on the Spark driver node for Ray programs called Ray context. Rayon context will automatically launch Ray processes alongside each Spark executor, namely Ray master and Raylet, and it also creates a Ray manager inside each Spark executor to manage the Ray processes. Ray manager will automatically shut down the Ray processes while the program exists. Users can control the start and stop of Ray provision by simply calling Ray context APIs inside their application. Also, data is shared between Ray and Spark through Plasma, so operations of Ray and Spark can be integrated into one pipeline in the application. It is very easy to use Rayon Spark. First, you init the Spark context. Then you construct the Ray context with the Spark context you have. Then you can run whatever Ray programs you like or mix your Ray program with Spark programs. or you don't want to use rate anymore, you can call rate context.stop to stop the rate cluster. Okay, now so far we have finished all the background. Now let's come to the core part for Scalable AutoML for time series on rate. Well, this figure shows a high-level overview of the time series support in Analytics project. And the time series part is highlighted here in yellow. At the bottom level, there is a general AutoML framework, which provides abstractions of machine learning pipeline stages and automates processes such as feature generation, model selection, and hyperparameter tuning. On top of that, we provide algorithms and models specifically for time series, including forecasting and anomaly detection. And then our users can build applications on top of those for different usage scenarios. There are three major features in our solution. First, that we provide rich algorithms, which include state-of-the-art neural network models and hybrid models. And second, we have AutoML support, which automates the training process and saves the tuning efforts. And last, we utilize what's provided in Analytics Zoo to seamlessly scale the automated training in the big data cluster. Oh, here's a overview of the software stack. In the AutoML framework, you can see that there are four major components in blue. Feature transformer and model are abstractions of the machine learning stages. They can be considered as black boxes, which takes in a hyperparameter configuration to construct the internal pipeline and control the execution process. Specifically, feature transformers can do feature generation, rescaling, and feature selection. Models can do a single model training as well as multiple model selection. A search engine is responsible for generating hyperparameter combinations, spawning the trials, and scheduling the trials in the cluster. We have implemented Raytune search engine, which enables these capabilities on top of Raytune. And when the search finishes, the results of all trials are retrieved, and the pipeline is constructed from the best hyperparameters and the trained model. The pipeline can be saved to Fire and restored later for inference and incremental training. On top of this, of the AutoML framework, we have implemented some feature transformer and models specifically for time series, and a class called time sequence predictor to enable the automated training flow, and a class named time sequence pipeline for the pipeline output. Here's an illustration of the training workflow at runtime. So basically, we use a search engine to drive the entire training process. At the time of the construction, the search engine takes in a feature transformer and a model, and it also takes in a search preset to configure how to search the hyperparameters. At runtime, the search engine generates hyperparameter combinations based on the preset, spawns the trials, and schedules the trials on the array cluster. Each trial runs a different combination of hyperparameters, and when a trial ends, it will write these results to the HDFS. Finally, after all trials finished, all results are retrieved from HDFS and analyzed. Then the pipeline is constructed from the best hyperparameter configurations and the trained model. So here's a glimpse of the APIs. To train a pipeline, you first create a time sequence predictor, and then you just call fit on it to launch the automated training process. For fit, there is an argument called recipe, which you can use to configure how to do the hyperparameter search. We have implemented several handy recipes for your convenience, but you can always write your own. There's also a flag called distributed, which indicates whether you're running it on a single node or a cluster. The result of the fit is a time sequence pipeline, which you can save it to a file and load it later. The pipeline also has APIs like evaluate, predict, and fit for evaluation, prediction, and incremental training on new data, respectively. Last, I would like to introduce a new project which is built on top of our scalable AutoML time series supporting Analytics Zoo. The name is Project Wu. We have created this project specifically for telco applications. In Project Wu, we not only expose the AutoML capabilities for time series in the AutoTS module, We also expose some built-in model without AutoML. And we also provide some reference solutions for typical telecom use cases, such as network traffic forecasting. I'll talk about the details of this reference use case in the next section. Okay, now let's come to the last part, the use case sharing and learnings. So this slide shows a reference use case in a project of the network traffic KPI forecasting case. So before diving into the details of this case, let me first introduce some background. We know that many KPIs are collected from the telecom network, such as download and upload speed, channel utilizations, and number of connected users. Forecasting on such KPIs actually has very wide applications in telecom operations. For example, a real application that we have worked with our customer is to use KPI forecasting for energy saving. In that application, our customer tries to forecast KPIs for each cell in the base stations so that they can know which cells are expecting low service demand in the next day. Based on those KPI forecasts, they can schedule shutdown for individual cells so that they can save a dramatic amount of energy without much impact on the customer overall experience. Besides that, people also use traffic KPI forecasting for adaptive network slicing. So that is why we choose KPI forecasting as our reference example in the project Zhou. In our case, in Zhou particularly, we use a public data set which contains real-world network traffic data maintained by the wide project. We have used the aggregated traffic KPIs such as total bytes and average rates as example targets for forecasting. And we use data in the past week to forecast the traffic in the next 2 hours. We have provided 2 notebook examples to show how to use the KPI, how to use the Zhou APIs to solve this forecasting problem. One is to use the built-in forecasters, and the other is to use the AutoTS module, which has AutoML support. This reference case is so close to the reality that some of our customers has built their own applications from these reference notebooks just with slight modifications. This slide shows a project that we previously collaborated with SK Telecom. This is actually another type of application of KPI forecasting. In this case, SK Telecom uses KPI forecast to identify potential anomaly in cells and base stations and visualize them in a 3D map. The reason we make it an example is such kind of anomaly detection is very common in telco. Although this case itself is not implemented using the time series solution we talked about in this session, we do have other customers who are using our solution to work on very similar anomaly detection applications. SK Telecom has a talk in last year's Spark Summit, and you can know more details about this kind of application from that talk. Besides, in Project Zhou, we have a similar forecast model as the one used in this case, and it proved to work better than traditional models in our real customer use cases. Okay, now let's take a look at a real case which uses the time series solution introduced in this talk. This is a project that we collaborated with Newsoft, which is an IT service provider whose customers include some of the most famous German luxurious automobile manufacturer. In their intelligent AI ops system, they use forecasting and anomaly detection on the monitoring metrics for VMs and services. They use the results to generate alerts, help adaptive resource scheduling, and for visualization. In this case, they used our solution with AutoML to achieve the desired forecasting accuracy in a very short time. Okay, now here is a summary of the takeaways from our early users. So first, about some highlights. We found that it is an advantage that our models allow extra features besides the target value itself. For example, we have generated extra time-based features such as peak or off-peak hours, holiday, weekend, and our customers also have their own domain-related features. Such features can significantly improve the forecast accuracy in real applications. And with our provided models and automated training, most of the users can get a satisfactory accuracy faster than manual tuning. However, not all use cases can achieve a desirable result at the very early stage, and most of the time it is caused by poor data quality. Missing values plays a major part, and the ways to fill the missing values could have huge impact on the accuracy results. Another problem many customer faces is the large scale of data. And the problem is often not with the time dimension, but that there are too many time series to forecast. For example, one of our telecom customers have hundreds of thousands of cells, and each cell has several KPIs to forecast, which adds up to millions of time series to forecast at a time. And similar things happen in the VM metrics forecasting and the cloud settings. At such a large scale, it is clearly not efficient to build one model for each time series. We have been working on this problem and got some progress. Okay, now the future work. First is that, as I just said, we have been working on solving the problem of extremely high dimensional time series forecasting. And we also plan to improve the search algorithms, add meta-learning and ensemble components. And we're adding more models and features for time series based on customer requests. And we're also considering the possibility of adding automatic data pre-processing, which improves the data quality, especially missing value imputation. Okay, now that's all of my talk. Thank you very much.